everyone, and welcome to Okuma's Houston Tech Center. I'm David Fisher, lathe product specialist at Okuma America, and I'm with John Weniger, field sales engineer at Allied Machine and Engineering. Today we're going to do a live demo on Okuma's LU7000 EX 4-axis turning center. And we'll be featuring Allied's hole-making solutions. So in a moment, I'll be covering the details on the machine itself, but for now I'm going to turn it over to John and let him talk about Allied's drilling tools.
Thanks, David. Like he said, my name is John Weniger. I'm with Allied, and I'm a field sales engineer up in the Dallas market. So we're going to go over some of the tools here today that we're going to run on this machine, on the LU7000. First, we're going to talk about our APX drill. So this is a modular style drill. It runs from 1.3 inch diameter out to about 4 inch diameter on the upper end, about 33 millimeter out to 101.6. It'll go from 3, 5, 8, and 10 times diameter. Great for deep hole drilling and when it comes to removing a lot of material quickly. This is the tool to run. So we're going to switch to the overhead cam here and look at the head. So on the back half, you can see here, this is our X style connection that'll actually lock into the holder. Very strong, robust connection, and it's a modular head, like I said. So in case you damage the tool, damage the head itself, you can remove that head and you can put another one on, and you're up and running with limited machine downtime. The center insert here, this is our TA style head that runs our TA inserts up front. Gives you the option to run carbide or cobalt. For the cobalt would be less than ideal machining conditions in terms of centering. You can also run our Genesis style insert, which is our cam style insert for higher penetration rates up here in the pilot insert. As we move to the outer edge, this is a 3-inch diameter head, so it's going to be single effective. It'll use one insert here in our inboard pocket, and then when we flip the tool, it'll run one insert in our outer pocket here. Same inserts, and when we move to single effective, we introduce a wear pad. You can kind of see it right there. So this is a great style tool when it comes to, like I said, removing a lot of material quickly. Lathe applications or mill, it's straight shank as well as Cat 40 and Cat 50 as a stock solution. Our second tool we'll be highlighting today is going to be our opening drill. So that's a great tool. It's 2-inch diameter on the low end out to about 5.6 inches on the high end. That full diameter range is covered by the same single insert for the complete range, and by 4 tools itself for that entire range. Straight shank, cat shank, HSK, you name it. We have a lot of different shank options with this style of tool. It comes in short and long lengths. So we're going to move to the overhead camera again, and I'll give a quick breakdown on how this tool adjusts and works. So how this is set up, it's a cartridge-based tool that uses these socket head cap screws to bolt these cartridges on. It adjusts similar to a twin cutter, where you'll adjust this here against a pin, and this will move this cartridge out. You'll set this to your finish OD. You'll flip around to this other cartridge, and this just kind of gives a demonstration how that tool slides. And you'll pull this cartridge in about 180 thou from your finished cartridge, just to cover the gaps within your inserts. And then you'll lock it down here with your socket head screws. So a great tool when it comes to lathe applications, when you're taking multiple boring passes, as well on mills when you're talking about a lot of feed milling and you want to eliminate some of those tedious processes, and can introduce a tool that can one-shot that application, remove a lot of material quickly. Our third tool we'll be highlighting is our new TA Pro drill. It's about 437 on the low end of diameter range out to about 1.8 inches on the high end. Straight shank as well as cylindrical shank, imperial and metric, anywhere from a stub all the way out to 15 times D. I'll go to the overhead cam and show the features of this tool. We've redesigned the holders as well as the inserts. The holders are going to have a deeper gullet cut into them to allow for maximum chip flow back out of this tool when drilling. And on the back, if you can see here, this is a dual gun drill tool. So it'll have one gun drill that'll feed this upper insert. There's this upper flute. You'll have 2 different outlets. Likewise, on the other flute, you'll have the same deal. Two different coolant outlets. The inserts are also redesigned as well. We have P for an ISO grade insert for P, which will be for your steels, a K for your irons, an N for your non-ferrous, and those are our carbide grades. And we also have an X geometry, which is our cobalt offering for less than ideal machining conditions. So a great tool that is a buff from our existing TA product line. So let's go back to David, and we're going to learn a little bit more about this machine now.
All right, thanks, John. Heading over to the machine. So the LU7000 EX is Okuma's largest 4-axis turning center. With a heavy-duty, massive cast iron base, box-weight construction, this machine tips the scales at over 88,000 pounds. So it's a beast. Building on that, we provide a wide range of spindles so this machine can be tuned to customers' requirements. So for example, aerospace industry need lots of power. We can provide it. We provide spindles with over 10,000 Newton meters of torque to handle those high temperature nickel-based alloys and other difficult to machine materials. Moving back to the oil patch industry, there we need large through holes. And again, we can provide it. We have various spindle bores available, all the way up to 22 inches for large pipe applications. For flexibility, this machine has a milling turret. So 20 horsepower, BMT, rigid connection. We can do a wide range of mill drill applications. So if you have a large part, you don't want to move it from machine to machine, we can do it complete here. We do also offer a Y-axis option, and we can provide turning only generally for pipe field applications. Then on the lower turret, we have a wide turret, super rigid base, ideal for those applications where you have to deal with chatter, large boring bar applications. This provides a nice rigid base for those types of machining processes. And finally, we have our heavy-duty tailstock. This is a fully programmable tailstock with a 7-inch quill, so ideal for large, heavy-duty shaft applications. So in a nutshell, that makes this machine a great machine to push tools to the limit. Obviously, I've only covered the surface here. If you need more details, please go to okuma.com where you can get full specs on this machine. Now, I'm going to turn it back over to John. John, what are we going to see here today?
Yeah, so this is a beast of a machine. I'm ready to see what this thing can do. First operation, we're going to run a 3-inch diameter APX drill through the center of this part. We're going to follow that up with a 4.5-inch diameter opening drill to come through that existing hole. And then finally, we're going to run a bolt hole pattern at 1 1/8" diameter with our TA Pro. So I'm geared up.
Awesome.
I'm ready to see some chips.
Great, let's do it. Okay, and welcome back. And it is time to make some chips. So for this part of the demo, I'm joined by Rob Brown with Allied. And Rob, why don't you go ahead and introduce yourself?
All right. Well, good morning, everyone. My name's Rob Brown. I'm the engineering trainer at Allied Machine and Engineering, and we're quite excited to be able to make some big holes today. We're going to be throwing a lot of chips against the glass, so I'm pretty excited to get to run some demos. But before we do that, Dave's going to kind of talk us through the turning operations that were done on the tools, or on the parts that we're going to be doing today. So Dave, if you want to go ahead.
All right, thanks, Rob.
Take care of that.
So for the turning portion of the demo, we've got a solid billet 4140. We're going to make a couple of turning passes. To keep things simple, we're just going to use the upper turret for that. You can see the lower turret in position, so we've got that synced up, ready to go for the turning passes. Right now we're running 500 surface feet, 15 thousandths per rev, and we're about to finish up here. Like I said, in the lower turret is just waiting for a matching sync code, the upper turret, to begin the pinch turning operation. Okay, so now we're running again at 500 surface feet, but 30 thousandths per rev. Of course, we have two tools in the cut. So our chip load is 15 thousandths per tool. Basically, we sync up the turret when we need to sync it. So we have our sync code set up at the beginning of each pass, and then we just turn the tools loose to make that cut. Since we're pinch turning, we don't have any issues with surface footage differential, but if we did, Okuma has M codes to give surface footage priority to either the upper turret or lower turret as the programmer deems is the best for the application. And then as we do our finish pass, again 15,000 per rev, 500 surface feet. We're using a single turret for that. Of course, we could use two. It just depends how you want to set it up, whether you want to keep things simple or minimize your cycle time. So, okay. So I'll turn it over to John to cover the drilling.
All right, well, once again, we're getting ready to do some drilling. It was kind of cool to see all the turning work that went into prepping the parts to get ready to machine this. What we're going to start off with is using our apex drill. The tool diameter is going to be a 3-inch diameter, which in metric is 76.2 millimeters. We're going to be going a depth of 7.5 inches, which is about 190.5 millimeters deep. The speed and feed we're going to be running is 500 surface feet per minute, which is 152 meters per minute. Feed rate is 7 thou per rev, which is 0.18 millimeters per revolution. And what we're using today is going to be our standard apex head, and the body is a 3x D body. So Jake, if we're ready to go with this demo, let's go ahead and fire it up. And once again, we're doing a 3-inch diameter, 4.5 inches deep, running 500 surface feet a minute, 7 thou per rev. And we'll just kind of see how this goes as we go. And you can see the tools already, or the workpiece has already been prepped with all the turning that you saw just a minute ago. So we're ready to go whenever we get there. The coolant on this is 100 psi of coolant pressure. It has a significant amount of flow because obviously these are some large diameter tools. So the flow going through these tools is pretty extreme for the pressure that we've got going on. And just to give you the details again, 3-inch diameter, 76.2 millimeters per diameter, 76.2 millimeters. The depth is 7.5 inches, which is 190.5 millimeters. Running 500 surface feet, which is 152.4 millimeters in diameter. 7 thou per rev, which is 0.18. So that comes out to about 4.5 inches a minute. So it's going to take about a minute or so, or a couple of minutes to get the hole drilled once we get going here. And once again, as John and David talked about whenever we were leading up to the demo there, the machine we're on is quite a bit larger than what we're normally used to running on. The LU7000 is quite a bit larger than the lathe that we have back in the lab in Ohio, so I'm really glad that Okuma gave us the opportunity to run this application on their site. So,
are you doing a restart?
Yeah. And as happens in live demonstrations, we appear to have an alarm going off. So this is where I get to tap dance through this. So, as Jake's trying to get the thing to reset, and that's what we're going to do. But while we're waiting, you know, John kind of showed you this tool earlier, but the Apex, the particular one we're going to be running, has a TA pilot on it for the stability that it creates, and then it has 2 outboard inserts that are offset. The Apex tools are available from 33 to 101.6 millimeters in diameter. The ones that are 33 to 70 millimeters, the inserts on the outboard are actually balanced, and then once we go above 70 millimeters, which is about 2 3/4 inches in diameter, that's where we go to the unbalanced cut. That reduces the horsepower draw on the machine, as well as allows you to get more coverage with the inserts that are being used. Whenever we go to the ones that are over 2 3/4, that's where we put the guide pads on the tool. And it sounds like we've got power, so we're going to take a look at what goes on here. So let's go back to the demo. Once again, this is a 3-inch diameter APX, running 7.5 inches deep. Oh, stop the application. Stop. Don't drill with it. We need the other tool to come in first. Yeah, that tool is designed to open the hole. Okay, well that was about to get exciting. So we're going to rotate around to the Apex tool because we've got to put the hole in it first. The opening drill, based on the name, only opens up a pre-existing hole. So the demo would have been over really quick if we would have actually touched down with it. So he's just got to rotate the turret around to the proper tool, and we'll see what we got going on here. Okay. So let me take a look here. Yep, we got the Apex in there now. So let's fire that one up. So now let's put a hole in this. So 3-inch diameter going 7.5 inches deep. It's got a TA pilot on it. The pilot is a TC geometry to make nice little small chips. So we're going to actually see 2 different styles of chips with this tool. We're going to see the chips that the TA creates, which are going to be nice little small chips. And then we'll see the chips that are made by the outboard inserts, which are going to be larger chips than that. So what you notice is it's really quiet. We don't have a lot of noise while this tool is running, and it's a nice steady load. There's not a lot of vibration. It's nice and quiet. And you can see we got a lot of coolant flow going through this tool. So that helps keep those chips moving, so we don't have any worries about chip evacuation issues with it either. Okay. And, you know, obviously this machine is a pretty large machine, so we've got plenty of power to run these larger tools, which, you know, as I said, I appreciate the fact that Okuma allowed us to come here and run today, because honestly, we can't run a tool this large in our lab because our machines are not large enough to be able to do that. So, and remember, we're doing a 3-inch diameter, 76.2 millimeters, 7.5 inches deep, which is 190.5 millimeters. Running a speed of 500 surface feet, which in metric is 152.4 meters per minute. Speed rate of 7 thou per rev, which equates to 0.18 millimeters per revolution. So the total cycle time for this application is probably somewhere right close to 2 minutes. It's going to be a little bit less than that, but it's pretty close to a 2-minute cycle time. And so whenever it's done, we'll take the tool and we'll open up the doors. We'll grab some of the chips and take a look at them, and see how they came out, and then kind of get prepped to come in with that tool we tried to run the first time. We got to make sure we have the hole there already. So you can see the chips are still coming out. We've got a nice coolant flow going through this. You know, one of the nice things about an APX drill is that the flutes are really large, so there's plenty of space for all those chips to be moved out of the hole. So there's plenty of area for chip evacuation here. Okay. Once again, notice it's still nice and quiet while it's running. You may hear a little bit of a chirp when it breaks through on the back side, because we are drilling a through hole. Okay, and there it goes. So now we're going to bring the spindle back down. We're going to pull the tool out of the spindle. We'll gather up some of the chips. Jake's going to be kind enough to grab for us, and we'll take a look at those underneath the glass. So we're doing our retraction out of the workpiece right now. And whenever this is all done, obviously this part's a bit heavy for us to throw it underneath the camera here for you to see it. So we actually have a tool or a part that we ran off whenever we were kind of prepping this job. So we'll show you that afterwards, what that looks like. Show you the quality of the hole, the quality of the outcome whenever that happens. Just for your reference, we are drilling at the 4140 alloy steel, about 200 Bernal in hardness. So that's what we got going on. So we'll have Jake open up the doors for us here and grab a hold of some chips. And we'll take a look at those underneath the camera. So, I'm going to just grab a handful of chips there, Jake. Just throw them on the towel there. Thank you very much, sir. Let's take a look at what we got here. Okay, so remember I told you we had chips for the TA and chips for the Apex. So these little chips here, this is the TA chip that we would get, a nice small chip using our TC geometry insert. Then we come in with the Apex, and those are taking out quite a bit of material, as you can see here. You can see what the chips look like for that. Some of them are broken up nice and small, some of them are a little bit big. But what you got to remember is whenever we're talking about the flutes for the APX drill, nice big open gullet, so big chips like this aren't going to get you in any kind of trouble. So now we're going to get ready to do demo number 2, which is coming in with our opening drill. And basically, if you really think about it, what the opening drill is kind of like a rough boring tool, but it removes a lot of material. You can remove up to about 87 millimeters of material in one pass. Is about the max that you're going to be able to do with the opening drill. So what this allows you to do is it allows you to, instead of stepping out that hole, we're able to come in and basically produce that finished size. So remember, 4140 alloy steel, 200 Bernal. We're coming in with a 4.5-inch diameter opening drill. That's 114.3 millimeters in diameter. We're going to be cutting it 3 3/4 inches deep, which is 95.25 millimeters. Speed and feed, that tool is going to be running at 750 surface feet, which is about 228.5 meters per minute. Feed rate of 4 thou per rev, which is 0.1 millimeters per minute. And Jake, if you're ready to bring that one around and run that, let's go ahead and take care of that one. So the inch per minute on this one is going to be about 2.5 inches a minute, or about 65 millimeters per minute penetration rate. So going at 3 3/4 inch depth, it's going to take, roughly, once again, somewhere in that neighborhood of 1.5 to 2 minutes to cut the hole. So we're going to bring it in, and like I said, what we're going to do is we're going to open up that 3-inch diameter hole up to 4.5-inch diameter. So we're going to be removing quite a bit of material with this thing, okay? So, and remember, whenever you set the opening drill up, both pockets are adjustable on this. What you do is you set your major diameter on one side, and then on the other side, what you're going to do is an offset between 160 and 200 thousandths of an inch. And what that does for you is that allows you to get the offset with the insert, so you get complete coverage, so it cuts the entire cut. So, as you're seeing, we're making the chips now. Remember, the speed and feed, we're running 750 surface feet a minute, 4 thou per rev, which in metric is about 228.5 meters a minute at a feed rate of 0.1 millimeters per revolution. Now, once again, as you listen, everything's quite quiet here. Everything's running nice and quiet. What that means is our surface finish is probably going to be quite nice. The chip formation that we're getting off this is, maybe a little bit stringy, but remember, this is 200 Bernal 4140 material. So, the chip form on it is not going to be super optimum because it's not terribly hard. It's still in a somewhat gummy state. So, but it's running nice and quiet, and everything's running pretty much the way that it should. And whenever this one's done, just like we did before, Jake can grab a handful of chips, and we'll take a look at those underneath the camera here so we can see what it looks like. We're not too far from being to that 3 3/4 inch depth as we speak. And remember, we have about 100 psi of coolant, but on a tool that large, that turns into a pretty heavy amount of flow rate, okay? And that is going through the tool in these two applications because this turret does have coolant through capabilities on it. And once the spindle shuts down, we'll retract out. We'll grab up some of those chips and take a look at them. Okay? So we should be pretty close to the end here, based on time and how deep that tool is in the workpiece. There we go. So remember, we didn't drill all the way through because whenever we came in with the APX drill, we drilled 4.5 inches deep. So you'll be able to see the step that was created with the opening drill. And once this retracts out, like I said, we'll grab a hold of some of those chips and take a look at them. So Jake, if you want to grab a hold of a handful of those, and we'll take a look at those under the camera as well. Okay. All right, so once again, this kind of made a little bit stringier chips, and we're just going to take a look at a couple of them. But taking a look at what we got here, these chips, once again, with the opening drill, the inserts for that are quite a bit smaller than what we have for the APX, so the chip that it creates is going to be a more narrow chip because of the fact I don't have as large of a cutting edge. So this is what we got with the opening drill. But if you remember, whenever that ran, it was nice and quiet. Everything ran pretty well, and whenever we're done, like I said, we'll show you on a piece we made a day or two ago, prepping for this to show you the quality of the finish of the cut and everything else. So now we're going to move on to demo number 3. Demo number 3 is actually using the other spindle in the machine, and what we're going to be using there is our TA Pro. It is an M geometry TA Pro, or no, it's a P geometry TA Pro, I'm sorry. So this is going to be one that's got the so what that means is it's based on ISO classification, so the geometry, substrate, and coating is designed to be run in steels. So once again, 4140 alloy steel, 200 Bernal. The diameter we're cutting for this one is going to be 1 1/8 inch diameter, and what we're going to be doing is like the flange bolt holes around the outside of this pretend workpiece that we made up for this application. So for that 1 1/8 inch, going 3 inches deep, that's a 28.5-ish millimeter diameter, 76.2 millimeters deep, running 320 surface feet and 12 thou per rev, which is about 97.5 meters a minute. Feed rate is 0.3 millimeters per rev. This particular spindle, since we're using the other one, instead of having cooling through, what this is going to be doing is flooding. So we're going to be running a flooding application for this 1 1/8 inch diameter going 3 inches deep. So Jake, if you're ready to bring that one in, we'll go ahead and run that one. And we pre-drilled, it's an 8-hole pattern. We went ahead and drilled 4 of them to try to cut down on some of the cycle time that we have for this live event. So whenever this starts running, we're going to machine the other 4 holes. So remember, this is live cooling coming in from the top side. It is running a flood cooling application. Okay, so we're going to run 3 inches deep, which is about 97.5 millimeters, or I'm sorry, 76.2 millimeters deep, 1 1/8 inch diameter, which is roughly 28.5. Okay, so this one's going to sing for just a little bit here, but you can see the chips coming off of it. But remember, we're flooding externally here. So if we were running through the tool, I'd actually probably have a little bit better chip formation, so I have the coolant right where I need it to be. But that flange is 3 inches thick. So we're doing a fairly deep hole with this tool through those flanges for an 1 1/8 inch diameter, running a flood application. Okay. So once again, the depth of the cut, 3 inches, running 320 and 12, which is 97.5 and 0.3 millimeters. Okay. And obviously on this machine, we don't have any concerns about the power, because obviously if I can run a 3-inch APX drill, I can certainly run an 1 1/8 inch solid carbide TA Pro drill. Okay. So it looks like we're just about done with this hole. There it goes. Okay. So there we go. So now we're going to come around and do hole number 2. And remember, it's an 8-hole pattern, but we already drilled 4 of the 8 holes. So here we go with hole number 2. And remember, 3 inches deep, 1 1/8 inch diameter, which in metric is about 28.5, 28.6 millimeter diameter, going 76.2 millimeters deep. Okay. So as John pointed out, whenever he was talking about the products at the very beginning here, when he was doing the round table with David, he talked about the fact with the TA Pro, not only has the insert been redesigned, because now we have those ISO specific inserts they're kind of optimized for the type of material that you're going to be machining. They also redesigned the holder to make it so the holder has more resilience. It's a stronger body. It has more coolant flow capability, about 25% increase in coolant flow. The flutes are larger as well. So what that means is since I have larger flutes, I can put more chips into the flutes without worries of having any kind of chip packing problems or anything like that. So it works out quite well. Like in this instance where we're flooding quite deep, since I have those large flutes, I have less issues with worrying about chip evacuation problems for those applications. Now, it would be obviously a bit better, and you would get more longevity out of the tool if I were able to run through the tool. But the tool works quite well considering the depth of cut that we're going with the flood. Now, the little chirp you hear at the backside, that's the breakout of the tool whenever it breaks out the back of the hole. So this is going to be our last hole that we're going to do in this part. And then once again, whenever we're done with this, I'm going to have Jake grab a handful of those chips so we can take a look at them. And we're going to go and take the camera over to the workpiece that we did previously so we can show you the quality of the outcome. Okay? So the tool, while it does, it is making a little bit of noise and stuff there compared to the other two applications that we ran. You got to remember we are running a flood application here, and the TA Pro is working quite well in the application that we're running here. Okay, so that's the last hole. So we're going to have that back through here. Like I said, I'm going to have Jake go ahead and open up the doors once everything settles down, and we're going to take a look at the chips that we did, and we'll look at those underneath the camera here and see what we got going on. So Jake, let's just grab a handful of the TA chips. Yeah, this machine has a bit of a deeper bed than what we're used to whenever we do our demos for these live streams like this. So Jake's having to do a bit of a reach to get down there to get a hold of some of these things. That's fine there, Jake. Just need to show him some examples of what it looks like. Thank you very much. Okay, so let's take a look at what we got. Now remember, we're running flood, so these chips are getting quite hot. Okay, I believe that was one of them that came off of that. But you can see the heat that we're getting off the chips there and everything. That's because, obviously once it gets probably about 2 inches into that 3-inch deep hole, there's a whole lot of coolant getting down there. So that's why it's actually a good thing to have a carbide insert for an application like that, because of the fact we need something that's going to have better heat resistance than, let's say, we're running high-speed steel. The tool life would be quite short because of the amount of heat that gets generated. So we're going to pop this camera off here, and I'm going to take it over so I can show you the quality of the outcome. So get this out of here. Oops. There we go. Okay. So let's take a look at what we got. And I'm going to try to do this as well as I can. I am not a professional camera person, but you can see, like, this is the hole that we did with the opening drill. Let's see if I can hold this with one hand and kind of point with the other. So you can see the quality of the finish that we got with the opening drill. I kind of go overhead here. This is the hole. You can't see because of my arm, but you can see this was the pre-drilled hole that we did with the APX drill. So you can see how much material we removed in one pass with that opening drill. There's quite a bit of material that we took out. The quality of the finish is really, really nice, considering this is just basically a roughing tool for removing a lot of material all at once. So now we're going to move down here and take a look at the holes that were done with the TA Pro on the outside. Now, the finish quality on these holes isn't quite as good as what we got with that opening drill just a minute ago. But you got to remember, here I had through tool coolant. When I was machining this hole here, I was running flood, so that's going to have a negative effect on the quality of the outcome of the finish that we got. But in our pretend part that we're doing here, and we're going to kind of move back over here, on the pretend part that we were doing there, those outside holes were basically bolt holes for the flange. So as long as you have a drilled hole finish, that's generally going to be good enough. So that's the demos that we have for you today. I'm going to bring David back in here for a couple of minutes. And David, I just want to say thanks for letting us come down and punch some holes in your machine, throw some chips against the glass. Once again, since we don't have any machinery in our lab that's able to let us show you the drilling with the larger tools that Allied has in our hole making catalogs, I appreciate the time that you gave us to let us come and run here.
Hey, Rob, it's been great working with you guys. I mean, we love working with our partners. It gives us a chance to learn about your capabilities, and it gives you a chance to learn about our capabilities. So it's really been great. So thank you for providing the tooling for this demo. And as I said before, to get more information on the LU7000 as well as all the Okuma turning product, you can go to www.okuma.com and get all the details there. So,
okay, and obviously for Allied Machines products, make sure that you go to www.alliedmachine.com. We've got plenty of information, lots of videos, all kinds of good stuff on our website. And once again, thank you to Okuma for allowing us to use their facility today to do this live stream. And Jake, thanks for running the machine for me. I appreciate it. And I hope you guys all have a good day. Thank you very much, and we'll talk to you later.
Thank you.